It's February 2013, and at Vandenberg Air Force Base in California, a lone rocket stands poised under a cloudless sky.
T-minus 10, 9.
As the countdown begins,
7,
there's tension in the air.
5.
It's a perfect day for going into space. But with so much riding on this one launch, there's good reason for mission controllers to be nervous. The Atlas V rocket carries an advanced space explorer, one with cameras that can peer in multiple wavelengths and reveal hidden details the human eye can't see. If this mission fails, decades of groundbreaking science will be in jeopardy. But if it succeeds, it will vastly strengthen our understanding of the most interesting planet in the solar system. The planet is Earth. And the mission is just the latest in a long line of spacecraft that have transformed the way we look at our home world. And that is precisely why there's so much at stake now. This mission, Landsat 8, is not just about launching another satellite, it's about preserving a data dynasty. The Landsat program has already been running for more than 40 years, providing an unbroken record of our planet during a period of astonishing change. Now, with Landsat 8, researchers hope to extend that record for many years into the future. In the process, they may witness a transformation more profound than anything that was imagined when the Landsat program first began. It was a beginning inspired by a very different goal. In the early 1960s, the Soviet Union was leading in the space race, and the United States was sparing no expense to overtake its rival superpower. The objective was to be the first to land a manned spacecraft on the moon. But along the way, the US first had to master the basics of getting its astronauts into orbit. The first flights were solo and brief. Astronauts had relatively little time to absorb the incredible views that they were getting as they looked down on Earth. But that began to change in 1962, at the tail end of the Mercury program. By then, US astronauts were equipped with high-quality handheld cameras, and they had the time to use them. The final Mercury mission lasted over 34 hours. The photographs that resulted were amazing, especially in an era when scientists were still using black and white aerial photos to study Earth's terrain. As the Mercury program transitioned into the Gemini program, the orbital flights got longer, sometimes lasting several days, and the pictures got even better. By 1966, Gemini astronauts had snapped about 1,100 images, training their cameras on mountains, lakes, deserts, and coastlines. Often their pictures brought into sharp focus remote regions of the Earth that were hard to access and poorly studied. These pictures were not only stunning, they were clearly useful for scientists. Before then, pictures taken from orbit had been used mainly to observe weather patterns. Now researchers were beginning to understand the benefits that might come from having a satellite dedicated to exploring Earth's surface from space. A leading proponent of the idea was William Pecora, director of the United States Geological Survey. Pecora could see that the space program had the potential to greatly improve our knowledge of Earth's agricultural and natural resources. And this was just when population growth and industrialization around the globe were making such information vitally important. So, in September 1966, Pecora pushed the U.S. Department of the Interior to unveil a new program of space-based observation. Its centerpiece was called the Earth Resources Technology Satellite. But not everyone was enthusiastic about the idea. With NASA already deeply invested in a manned mission to the moon, government administrators were reluctant to spend still more money on another completely different space project. Others worried about the legal and political implications of launching a satellite that could see the territories of other nations up close from orbit. And then there was the US military, which had already been operating its own series of spy satellites since 1959. Defense officials were not at all eager for the public to grasp the remarkable power of surveillance from space. Despite these obstacles, the idea of an Earth-observing satellite for civilian use gradually gained support. In 1970, NASA got the green light to build such a spacecraft. Its design was a modified version of the weather satellites which had already been flying since 1964. But this spacecraft was equipped with cameras capable of imaging features on Earth's surface down to 80 meters in size, both in visible light and near-infrared. And it included a tape recorder for playing back data gathered from virtually any point on the globe. Assembly proceeded rapidly, and on July 23, 1972, the Earth Resources Technology Satellite, ERTS-1, was successfully launched into orbit. Sadly, William Pecora, the geologist and federal administrator who had pushed so hard for the mission, had died in hospital just a few days earlier. He was 59. Pecora never had the chance to witness the scientific returns from the satellite, which was later renamed Landsat-1. But the returns were impressive. And over the next 5.5 years, Landsat-1 would provide a treasure trove of data about our planet. And it was not alone. In 1975, Landsat-2 was launched, adding to the program's reach and extending its lifespan another 5 years further into the future. That pattern would continue with a series of overlapping missions into the 80s and beyond. And not a moment too soon. Landsat may have been born out of the space race, but it would come of age just as scientists were racing to understand profound environmental changes taking place on Earth. Thanks to Landsat, they would have a front row seat. Off the coast of Labrador, a tiny speck of land less than 50 meters across pokes up above the frigid waters. Uncharted after centuries of maritime exploration, it was finally spotted by Landsat-1 in 1976. To this day, it's called Landsat Island. Since it began in 1972, the Landsat program has added countless details like this to our map of the world. Yet the real value of the Landsat program comes not from putting new places on the map, but in seeing what's on the map in an entirely new way. Every Landsat spacecraft is equipped to see Earth's surface in multiple wavelengths of light, including some that are beyond the range of normal human vision. By assigning different contrasting colors to these wavelengths, it's possible for researchers to bring out details that would be too subtle to spot in an ordinary color photo. Here, for example, a small but lush corner of Oman stands out in marked contrast to the barren desert that surrounds it. This region is different from the rest of the Arabian Peninsula because the mountains here capture monsoon rains during the summer, supplying water to a rich and fertile strip of coastal lowland. Elsewhere, this vividly colored section of Axel Heiberg Island in Canada's high Arctic shows the extent of icy glaciers, here seen in blue, among the island's rugged mountains, which appear in yellow. Landsat can also reveal other more ephemeral features. Here, newly transported river sediments form ghostly ribbons off the Mississippi Delta. While here, in the Pacific Ocean, about 600 kilometers west of Chile, wind blowing over a remote island forms a repeating pattern of eddies in the clouds. There's no question that Landsat has given us a dramatically different perspective on Earth's natural geographic diversity. But even more revealing is the way the program has documented humanity's growing impact on the planet. Sometimes change operates at such a scale that we can only grasp its true impact by observing it from space. Nowhere is this more true than the Aral Sea, once the fourth largest lake in the world, a vast inland sea that was the size of Ireland. Though it has existed for thousands of years, the Aral Sea has all but disappeared in just a few decades because the rivers that feed the Aral Sea have largely been diverted for irrigation. This succession of Landsat images captures the Aral Sea's disappearing act. As the waters shrink to oblivion, they take away a once thriving fishery and leave behind a barren, salty desert. Landsat has also proved crucial for documenting a very different kind of loss. In the Amazon basin, the program's satellites have witnessed the clearing away of vast swaths of rainforest for logging and agriculture. This sequence shows how that process has unfolded in Rondônia, a state in northwestern Brazil. The rainforest is first divided up in a fishbone pattern as logging roads extend into undisturbed territory. Then, the parceled sections of forest are systematically removed. Roughly 16% of the Amazon rainforest has disappeared since Landsat began imaging the region. Elsewhere, Landsat imagery has witnessed the ever-increasing scale of development around the planet. For example, the city of Las Vegas can be seen spreading rapidly across the Nevada desert, placing a major strain on water supplies in one of the driest regions of the United States. Meanwhile, halfway around the world, a new lake forms behind China's enormous Three Gorges Dam. Completed in 2012, this massive hydroelectric project displaced over 1 million people. Around the globe, the quest for energy and its consequences are a recurring theme, yielding some of Landsat's most arresting images. In the wilderness of northern Alberta, Landsat looks on as vast swaths of land along the Athabasca River are opened up for oil extraction. And along the Persian Gulf, the wealthy Emirate of Dubai, a product of the Middle East oil boom, shows off some geographic artistry by sprouting artificial islands in the shapes of palm trees and a map of the world. Yet it's clear that on the real world map, the continued use of oil and other fossil fuels is having a profound effect on the planet. Here, Landsat documents the startling retreat of the Columbia Glacier in Alaska. As global warming sets in, rapidly melting ice and rising sea levels seem to be the inevitable result.
Yet, just as our awareness was growing about the magnitude of this change, Landsat's invaluable perspective on our planet was at risk of disappearing for good. As humanity comes to grips with global warming, the ability to continuously monitor Earth's surface from space has become the essential starting point for any future efforts to manage the planet's resources and preserve its priceless biodiversity. The Landsat program is tailor-made for this purpose. Because Landsat images are relatively wide-angle, they don't show details as fine as individual trees or buildings. Instead, Landsat offers a big picture view that is intended to capture changes on a regional scale. Each satellite in the series was designed to circle Earth in a polar orbit, allowing it to image the world in a series of strips from north to south. Starting with Landsat 3, each satellite was placed in an orbit that is just over 700 kilometers above Earth's surface. The orbit is also synchronized with the Sun, so that each time the satellite passes overhead during the day, the local time down below is about 10 o'clock in the morning. The timing and positioning of the orbit means a satellite can image any particular spot on the planet every 16 days, and always at the same time of day. This is especially useful for tracking long-term trends, because every time an image is captured of a particular location, the lighting angle is about the same as the time before. Because of this visual continuity, the Landsat database becomes more valuable the longer it accumulates, which is why researchers were especially worried when Landsat 6 failed during its launch in October 1993. The Landsat program had already narrowly escaped being shut down for budget reasons, and Landsat 5, though still running well, had already been in space for 9 years. It would have to hang on 6 years more before the US was ready to fund, build, and launch Landsat 7 in 1999. That launch was a success, but a few years later, the failure of a crucial piece of hardware meant the spacecraft was partially blinded and its images incomplete. It would be a long, hard battle to get the next Landsat approved. By the time it was ready for flight in 2013, Landsat 8 was not only the most sophisticated satellite in the series, it was also a rescue mission for the entire program. Then, just 6 weeks before the big launch, Landsat 5 finally gave out. After a record-breaking 28 years of observation, it stopped communicating with mission controllers in January of 2013. That meant only Landsat 7 was left, and it was no longer operating at full capacity. So, by February, with Landsat 8 on the launch pad, the fate of the entire program hung in the balance. Charging skyward on a column of white smoke, the rocket carried its precious cargo into orbit. A short time later, the good news was confirmed. Landsat 8 was successfully launched, and its systems were operating normally. Scientists were ecstatic and relieved. Over the coming weeks, the new mission would show off its prowess, sending back images even more spectacular than those of its predecessors. By May, the satellite was fully operational and returning more than 400 images per day. These first images from Landsat 8 make it clear that the entire program has now begun a new chapter, and that Landsat's continuous coverage will likely prove invaluable as we move into an unprecedented period of global change. By now, Landsat is not the only eye in the sky monitoring our planet. Every minute, we are circled by a range of Earth-observing satellites, like Terra, a multinational spacecraft operated by NASA that has specialized sensors for monitoring environmental change. Or like Canada's RadarSat program, a series of satellites that can see Earth both at day and night. Its radar vision penetrates clouds and fog to create dramatic, high-resolution images of the surface.
Looking at how things have evolved since the early days of Landsat, it's clear that we're now in a period of specialized planetary monitoring, one that no single satellite could manage alone. But Landsat, with its ever-growing record of our world, still provides an underlying foundation for an entire system of Earth observation.
Ultimately, that is where Landsat's greatest impact lies. In starting the program decades ago, researchers were not just creating a camera for photographing Earth from space. They were, in fact, creating a new field of science, the science of remote sensing. And as the pace of environmental change quickens around the globe, it's increasingly clear that this is one science we cannot do without. High above a rust-colored planet, an alien spacecraft prepares for landing. It has traveled for nearly 9 months, hurtling through more than 500 million kilometers of interplanetary space. Now, as it plunges toward Mars, the robot visitor sheds its protective cocoon. Just 20 meters from the surface, it hovers, then carefully lowers itself on a specially designed hoist. For 16 seconds, the robot's fate hangs by a nylon thread. Then it touches down safely on Martian soil. Its mission has begun. A mission in the name of curiosity.
When NASA was looking for a nickname for its 2012 Mars rover, it could hardly have chosen a better one than Curiosity. 8 years before, its two predecessors, Spirit and Opportunity, had proved that roving vehicles could revolutionize our understanding of the red planet. With Curiosity, rover technology had advanced, and scientists were in the driver's seat.
Those scientists were guided by an ambitious goal. Previous missions had shown that in the distant past, Mars had standing water on its surface. Now, Curiosity would go one step further and try to determine if Mars could once have supported life. That's a more challenging question to answer, and researchers needed a bigger rover to answer it. At 900 kilos, Curiosity is the size of a small car, allowing it to carry 15 times more scientific hardware than previous rovers. It's the most sophisticated suite of instruments ever to land on another planet. And for the Mars program, it's a big shift in approach. Earlier rovers were designed to be like wandering geologists, traveling over the landscape of Mars with a toolkit similar to one that a human astronaut might carry. By comparison, Curiosity is an entire laboratory on wheels. Its equipment includes a laser capable of zapping rocks up to 6 meters away in order to read their chemical composition. And its 2-meter-long robot arm carries a camera and a spectrometer for examining the surface up close, as well as a drill for extracting rock samples that can be tested by various experiments inside the rover. This is a planetary explorer like no other. And so is the place it set out to explore. In planning Curiosity's mission, scientists spent years combing through satellite images looking for a landing site that might offer signs of a habitable past on Mars. The search led them here, to Gale Crater. It's 150 kilometers across, with a 5.5-kilometer high mountain rising from its center. Like most craters on Mars, it formed billions of years ago, when an incoming asteroid collided with the planet's surface. The force of the impact blasted a giant hole in the Martian bedrock. A crater on Mars is easy to understand, but a mountain inside a crater is much harder to explain. How could such a towering feature have grown out of a deep basin? Scientists now suspect the answer is that the mountain didn't grow at all. Rather, it was left behind as other material was removed. The theory is that sometime after Gale Crater formed, it was blanketed with dusty sediment. Eventually, layer upon layer of sediment filled the crater to the brim and beyond. Later, wind chiseled that sediment away. It scoured out the crater walls, but left a large mound in the middle. The mound's official name is Aeolus Mons, but NASA scientists have dubbed it Mount Sharp, after Robert Sharp, a pioneer of planetary geology. Mount Sharp is what brings Curiosity to Gale Crater. Scientists hope that by climbing its rocky flanks, the rover will be able to read millions of years' worth of geologic history, laid down one layer at a time. Some of those layers are plainly visible from orbiting satellites. The lowest layers are the oldest. They're of special interest because the data suggest they're made of clay, which means they were likely deposited by water long ago. Moving further up the mountain, other layers may reveal how those watery conditions changed over time. The upper reaches of the mountain appear to be made up of material that was deposited by wind once the planet became dry and dusty. From top to bottom, the mountain seems to present the complete story of Mars.
Full parachute is deployed. We are decelerating. We are in power flight. We're at altitude of 1 kilometer descending. Standing by for skycrane.
As soon as Curiosity landed, scientists were thrilled.
Touchdown confirmed. We're safe on Mars.
Not only had the rover touched down safely, Mount Sharp was in plain sight. It towered on the horizon in one of Curiosity's first pictures from the surface. But the mountain was 8 kilometers away, and scientists knew it would take the rover more than a year to get there. So before the long trek began, they decided to explore Curiosity's immediate surroundings. It was to be the first test of their new laboratory on Mars. But little did they know just how much that test would reveal.
Touchdown confirmed. Proceed on fire.
When Curiosity set down on the floor of Gale Crater, it became the 7th spacecraft to land successfully on Mars. But more than any of its predecessors, Curiosity was built to journey far beyond its landing site. The rover's main objective was to reach Mount Sharp and study its layered geology. Those layers could already be seen in the distance on the mountain's lower slopes. But before heading in that direction, Curiosity had a chance to visit other points of interest closer to hand. Just a few steps from where Curiosity stood, scientists could see where the rover's descent stage had blasted away loose dust and gravel. The exposed patches showed that the soil was only a few centimeters deep in this part of the crater. Below it lay what looked to scientists like a type of conglomerate rock, a rock made up of smaller pieces cemented together. This was intriguing, but Curiosity did not venture any closer, in part to avoid contamination from any lingering traces of rocket exhaust. Instead, scientists now had a different idea. Not far from where Curiosity landed, satellite images showed where a river had once spilled into the crater. The riverbed ended in a fan-shaped deposit, left behind by water spreading sediments out over the crater floor. It was always the plan to try to land near this feature, and now Curiosity was right on the edge of it. By using the satellite imagery as a guide, scientists could see that just a few hundred meters from the landing site lay a point where the river deposit intersected with an older terrain. This looked like a promising spot to learn more about the ancient history of the crater floor, even though going there would mean driving away from Mount Sharp for a time. In the end, the detour would take far longer than scientists expected, but it would eventually lead to a big discovery. As Curiosity began moving over the landscape, it came across clues that pointed to an intriguing past at Gale Crater. There were more examples of the conglomerate rock that had been exposed at the landing site, this time jutting out of the ground like pieces of broken sidewalk. And when the rover zoomed in for a closer look, it found pebbles that looked rounded as though by water. This is typical of what is found in ancient stream beds on Earth. Already, the geologic story emerging from Gale Crater looked like an exciting one, but filling in the details would take time.
As they carefully gathered data, scientists were striving to understand if Mars could have supported life long ago. But given the rover's capabilities, there was also a more immediate question. Could there be something alive on Mars right now? And there was a chance that Curiosity might provide the answer by plucking it out of thin air.
For 10 years, scientists had been tantalized by reports of trace amounts of methane in the Martian atmosphere. The reports were mainly based on observations made from Earth, but the presence of methane was also indirectly confirmed by Mars Express, an orbiting spacecraft run by the European Space Agency. The Earth-based observations show that the methane seemed to be concentrated around particular features on the Martian surface, like these giant gashes called nili fossae. where spacecraft have also found signs of carbon-bearing minerals. If correct, this was a major find. On Earth, methane gas is produced by living things. It's a telltale sign of biological activity. Methane gas can also be produced chemically, but that requires the right kind of minerals along with water and plenty of heat. Either way, methane would mean that Mars was not a dead world, but a geologically and possibly biologically active one, somewhere below the surface. Now Curiosity was in a position to weigh in on Martian methane. Unlike earlier rovers, it had the technology to directly measure the chemical composition of the atmosphere. Over an 8-month period, that's exactly what the rover did. The result was a surprise. The rover found no significant amounts of methane on Mars. Either the methane reported earlier had completely vanished through some unknown process, or, because of a misreading of data, those earlier reports were wrong. This is not the first time Mars has given scientists contradictory evidence related to alien life. But with the methane question out of the way, at least for now, Curiosity still had plenty to do. And its exploration of the Red Planet was about to take an exciting turn at a spot called Yellowknife Bay. More than 2 months into its mission at Gale Crater, NASA's Curiosity rover stopped to capture a breathtaking panorama. The result is this mind-blowing 1.3 billion pixel image. It's the most detailed picture ever taken from the surface of Mars. By this point, the rover had driven about 400 meters. Not a great distance, but a journey with many stops that allowed scientists to gather data about the geologic history of this unusual site. To the right lay the rising slopes of Mount Sharp, the rover's ultimate destination. But straight ahead, scientists could now see a dramatic change in scenery. Here, the gravelly terrain that the rover had been traveling on since it landed ended abruptly. Up ahead lay a more complex-looking surface, with different layers of rock exposed in the form of assorted steps and slabs. Scientists were keen to explore this location, which they called Yellowknife Bay. The name is a tribute to the capital of the Northwest Territories, a frequent jumping-off point for geologic expeditions in Canada's north. By now, they'd had a chance to zap a rock with the rover's onboard laser and scoop up some soil for analysis. But neither the rock nor the soil could tell them much about Gale Crater. That's because the rock had been blasted there by a meteorite impact, while the soil had been carried in on the wind. So to understand the hidden history of the crater, Curiosity needed some local bedrock to drill into. It began by sidling up to this intriguing outcrop, made up of thin layers of sedimentary rock. Some of the layers were at different angles, suggesting the rock was made from sediments deposited by flowing water along an undulating stream bed. After a close inspection of this outcrop, Curiosity worked its way downslope to find an underlying layer of sandstone. And beneath that, the rover found still another layer. This one was mudstone, a type of rock made of fine silt or clay that was deposited long ago, perhaps at the bottom of an ancient lake. The rock was threaded with veins of minerals, that were deposited by water flowing through cracks. And in some places, Curiosity could see spherules, little round balls of minerals that precipitated out of water. Here were signs not only of rock that formed in water, but that had been exposed to water at different times in its history. And here at last was a place where Curiosity could drill down to find out more. After carefully scouting the terrain, scientists chose a rock they named John Klein, after a deputy project manager with the rover mission who died in 2011. Using its robotic arm, Curiosity reached down and swiveled its drill into position. The drill punched a small hole into the rock, producing a tablespoon's worth of fine powder, which the arm delivered to the rover's onboard experiments for analysis. Unlike most of the Martian surface, the powder was gray rather than red in color. That meant the minerals inside the rock had been sealed off from the atmosphere for billions of years. Here was a rock that offered a direct connection to the past. In March 2013, 7 months after Curiosity arrived on Mars, scientists were ready to share their results. A detailed analysis showed that the minerals in the rock had formed in water that was much like fresh water on Earth, non-acidic and not very salty. Furthermore, there were chemicals in the rock that the right kind of microbes can use to drive metabolism. Curiosity had found the key ingredients that could have allowed life to flourish when there was water in Gale Crater.
For Curiosity, this was mission accomplished. While it's still not known if Mars ever harbored life, scientists can now say life was at least possible there billions of years ago.
With the discovery came the news that the rover's mission had changed. Having answered its original question, Curiosity would now try to find out where and how to search for signs of past life on Mars. By the summer of 2013, the mission reached a major turning point. After making several more follow-up measurements, scientists said goodbye to Yellowknife Bay forever and put the rover on course for Mount Sharp. The first phase of the mission was over, and there were new discoveries ahead. But before it left, Curiosity provided its own glimpse of life on Mars by using its robot arm to take this striking self-portrait at John Klein Rock. It may be a long time yet before we know if there ever really was life on Mars. But we know that Curiosity is there, and that's a terrific start.
For our prehistoric ancestors, recognizing patterns was a key to survival. As they made their way in the world, they saw patterns in the landscape, patterns in the weather, and patterns in the behavior of birds and animals. And when they looked up at the night sky, they saw patterns too. What they found is that the stars aren't spread evenly across the sky. Many of the brightest stars seem to be grouped in a way that naturally draws the eye. And as Earth turns, these stars seem to move together, reinforcing the impression that they are related. By playing connect the dots with these groups of stars, ancient people transformed them into pictures, often of mythical creatures and characters from great legends. We know them as the constellations.
The constellations are still with us today, and they're a reminder of our ancestors' enduring fascination with the stars. But there can be even more to these ancient star pictures than meets the eye. Sometimes, stars we see together in the sky really are related.
A case in point is one of the most familiar star patterns of them all, the Big Dipper. The name reflects the way these 7 stars are arranged in the sky. Together, they resemble the outline of a pot with a handle. There are other ways of seeing it, though. In some folk traditions, it's not the dipper, but the wagon or the plow. And for the ancient Greeks and Romans, it was the Great Bear, Ursa Major in Latin, the official name astronomers still use for this constellation. To modern eyes, turning these stars into the image of a bear seems a bit of a stretch. The bear is usually portrayed with the handle of the Big Dipper as its long tail, even though real bears don't have long tails. But the bear connection makes more sense when we consider that the ancient Greeks called this constellation Arctos, a name that gives us the word Arctic. Arctos, or Ursa Major, may be our link to a much older tradition of bear legends, one that stretches back to the end of the last ice age, when the inhabitants of Europe and Asia were nomads wandering in a great northern wilderness. Perhaps they were the ones who first connected the most powerful animal in their world to the most prominent star pattern in their sky. So it seems fitting that in more recent times, astronomers have learned that the stars of the Big Dipper are themselves a wandering band of stellar nomads. This became clear in 1869, when British astronomer Richard Proctor noticed that 5 out of the 7 main stars in the Dipper are all moving through space at the same speed in the same direction, like airplanes flying in formation. Proctor had discovered what we now call the Ursa Major Association. Half a billion years ago, these stars formed together in a cloud of gas and dust. Today, we can find the same kind of raw material adrift in other regions of our galaxy. One of the nearest is called the Taurus Molecular Cloud. In this gorgeous view from the European Southern Observatory, we can see sections of the cloud wafting across the starry background. Over time, gravity can concentrate dark clouds like this, turning them into clusters of brilliant young stars. But even though they are siblings, such stars are unlikely to stay together forever. Instead, star clusters tend to spread apart as they drift through the galaxy.
And that means the Ursa Major group may be a lot bigger than it seems, extending well beyond the 5 Big Dipper stars that Proctor once connected. Even Sirius, the brightest star in the night sky, was once thought to be a member of this group. More recent data now suggest it's too young to have formed along with the Ursa Major Association. In 2003, a detailed survey based on data from the Hipparcos satellite found that 59 stars are likely members. These stars are scattered across 30 light-years of space, with the center of the group located about 80 light-years from our solar system. In galactic terms, this is remarkably close. It's purely by chance that our existence happens to coincide with the moment when Earth is on the outskirts of this passing system. Millions of years from now, those stars will have moved on, and the Big Dipper will be no more. But astronomers have discovered that Ursa Major is not the only constellation with a hidden connection among its stars. Throughout history, when adventurers and traders headed east or west to distant lands, they knew they were bringing their constellations with them. As Earth turns, places on the globe that are at similar latitudes, like Europe, Asia, and North America, will see the same stars. But those who travel south experience something very different. Earth doesn't turn north to south, so there are stars and constellations that can never be seen from northern latitudes. It's here in the south that we find Centaurus. It's a sprawling constellation that the ancient Greeks pictured as a spear-wielding centaur, the imaginary creature that is half man, half horse. Like Ursa Major, the Great Bear, the outline of the centaur may not seem obvious to modern eyes. But there's no mistaking the 2 brightest stars in this constellation, known as Alpha and Beta Centauri. Together, they point to another group of 4 stars, which the ancients also imagined as part of the centaur. Today, we identify this group as a separate constellation, and it's one of the most famous, the Southern Cross.
Whether it's one constellation or 2, the combination of the Southern Cross with Alpha and Beta Centauri forms the dominant star pattern of the Southern Hemisphere. But how did the ancient Greek astronomers know about these stars, which can't even be seen from Greece?
The answer is precession. It's a term that describes a gradual change in the direction of Earth's axis as our planet slowly swivels around like a big gyroscope in space. Because of precession, the stars of Centaurus and the Southern Cross have shifted over the centuries. Once, long ago, they were visible from Europe. Now they've become, for the south, what the Big Dipper is in the north. Many of the stars in Centaurus and the Southern Cross are moving through space with a similar speed and direction. But this association is far younger than the Ursa Major group, and it contains stars that are much brighter. Many are blue giant stars, thousands of times more luminous than our sun. Blue stars burn out quickly. The hottest ones only last a few million years, a tiny fraction of our sun's age. As they use up their fuel, blue stars eventually expand and change into red supergiants. This has already happened to the brightest member of the group, the brilliant red star Antares. Antares is part of Scorpius, a different constellation, but its motion connects it to the stars of the Centaur and the Cross. Collectively, they are the Scorpius-Centaurus Association. The ultimate fate of these bright stars is to die in spectacular fashion. As each one runs short of fuel, its core will collapse, triggering a supernova. A violent stellar explosion that rips the star apart. The explosion produces a blast of energized gas that spreads out into the surrounding space for hundreds of light years. This, too, has already happened in the Scorpius-Centaurus Association. The entire group, including most of the stars of the Southern Cross, sit inside a bubble about 400 light-years across. Astronomers suspect the bubble was formed by one or more of the association's stars going supernova during the past 15 million years. The bubble can't be seen with an ordinary telescope, but in this map of the Milky Way in radio waves, part of it shows up as a giant loop in the foreground. Astronomers call it Loop 1. Our own solar system lies just outside Loop 1 in another smaller bubble. This local bubble may also have been caused by one or more supernovas, perhaps when the Scorpius-Centaurus Association was closer to Earth than it is now. This idea was strengthened in 2004 when researchers discovered a rare isotope called iron-60 in sediment deposited at the bottom of the Pacific Ocean. Iron-60 is produced in supernova explosions. This suggests that sometime in the last 3 million years, Earth was in close proximity to a supernova. Such an event may have had serious consequences for life. One group of researchers has even speculated that a major extinction of corals and other marine life about 2.5 million years ago was caused by a supernova blasting Earth's atmosphere with radiation, temporarily destroying the ozone layer. So far, this idea remains speculative, and there are reasons to be skeptical. Astronomers have calculated that a supernova would have to be within 26 light-years of Earth to cause such severe damage to our planet. While that's not impossible, a supernova going off so close to us so recently would be quite a coincidence. What we do know is that our planet did change at that time, with some creatures dying out and some new groups appearing, including the first members of our own genus, Homo. Whether our pre-human ancestors were somehow affected by a nearby supernova remains an open question. But when we look to Centaurus and the Southern Cross, we're reminded that hidden connections between the stars may sometimes include us. Winter in the Northern Hemisphere is the time when many of the brightest stars can be seen high overhead. Among them are Castor and Pollux. These stars, almost identical in brightness, are the Gemini twins. They're part of a constellation that depicts two brothers in the heavens. But these stars are not related. At just 34 light-years from Earth, Pollux is both closer and older than Castor, which is 50 light-years away. They are siblings in name only. It's the same story with another well-known winter constellation, Cassiopeia, named after a mythical queen. The 5 brightest stars in Cassiopeia form a W pattern that's easy to spot in the northern sky. But in this case, the grouping is pure coincidence. The stars in the W are spread out along a line of sight that ranges from about 50 to over 500 light-years away. They too are not related. Nevertheless, most stars must have relatives somewhere because stars tend to form in clusters within vast clouds of dust and gas. If we look towards the stars of the Southern Cross, we can see a recent example. Near the Cross, but 6,000 light-years further away, lies one of the greatest treasures of the southern sky. In the 19th century, astronomer John Herschel called this the Jewel Box star cluster. With its concentration of hot blue stars and bright red giants, the cluster reminded Herschel of a casket full of precious stones. Today, astronomers estimate the cluster contains about 100 stars that formed around 12 million years ago. As the cluster ages, the brightest stars will quickly exhaust their fuel and burn out, in some cases going supernova, like the stars of the Scorpius-Centaurus Association. Those stars that remain will continue to travel together, like the Ursa Major group. But over billions of years, they're destined to drift apart and lose each other among the stars of the Milky Way. Our own Sun is one such star. Now 4.5 billion years old, it too must have relatives somewhere out there in the galaxy. Some of those sibling stars could have planets and even life. Since life here is based on the chemical ingredients that went into forming the Sun, it would be fascinating to see what happened to the same ingredients elsewhere. But could we find the Sun's long-lost relatives? Are they hidden somewhere among the familiar constellations? One approach to answering these questions is to look at the nearest stars and see if any have strong similarities to our Sun. The nearest star of all is Alpha Centauri. Although it appears to the eye as a single point of light, Alpha Centauri is actually a multiple system made up of 3 stars in orbit around each other. The smallest is a red dwarf star, known as Proxima Centauri, because it's also the closest of the 3. The entire system is only 4.3 light-years from us. That's still thousands of times further than the most distant planet in our solar system, but for a star, it's very, very close. In fact, it's so close that Alpha Centauri can't be a member of the Scorpius-Centaurus Association. It just happens to be in the foreground when we look toward those stars. Similarly, someone living on a planet in the Alpha Centauri system would see our Sun as part of the constellation Cassiopeia, giving the W an extra zigzag. But even if such a planet exists, we already know that any creatures living there cannot be our galactic cousins. The Alpha Centauri system is older than the Sun, and it's moving on its own separate course. After its closest approach, about 27,000 years from now, the system will gradually start to pull away from us, and it will eventually fade into the starry background. Meanwhile, the search for our Sun's true siblings continues. In 2013, astronomers conducted a careful study of 30 stars known to have ages, compositions, and motions similar to the Sun. After a close examination, only one of the 30 qualified as a possible true sibling to the Sun. It lies just over 100 light-years away in the constellation Hercules. It doesn't have a name, just a catalog number, HD 162826. But this one candidate sibling could soon be joined by others. In December 2013, Europe launched the Gaia mission. It's a space telescope that will help construct a 3D catalog of nearly 1 billion stars, roughly 1% of the Milky Way's total stellar population. As never before, Gaia will reveal precisely where all the stars are around us and show us how they're moving. In doing so, it will reveal which stars are truly associated with one another, including those that might have a connection to our Sun.
Long ago, our ancestors looked for patterns in the stars, and they invented the constellations, groups of stars that have a story to tell. Now Gaia is giving us a more sophisticated way of observing the stars, but we're still looking for patterns.
What we find will reveal the unseen relationships among the stars around us and give us a new set of stories. It may even give us a story that includes us. The story of a great family of stars that formed together in a cloud, spread out into the galaxy, and along the way brought the galaxy to life. Not so long ago, astronomers thought they were getting close to understanding what the universe is made of. First, there's matter, which makes up the stars and galaxies that light up our night sky. Then, there's dark matter. It's thought to be an unidentified type of particle that gives off no light. But we know it exists because of its gravitational pull. Only recently have astronomers discovered that there's a third presence in our universe, and it's not any type of matter at all. It's a mysterious phenomenon that could literally be caused by empty space.
It's called dark energy, and its growing influence in the universe is so important, it will dictate the ultimate fate of everything else. The only trouble is cosmologists aren't sure what dark energy is, and finding out has become one of the greatest scientific quests of our time.
The seeds of the quest were planted nearly a century ago. That's when astronomers first became aware that the tiny blobs and swirls of light they could see in their telescopes were galaxies. Galaxies are vast systems of stars, like our own Milky Way, but far off in the cosmic distance. Here, the Hubble Space Telescope peers across the edge of the Milky Way toward the constellation Centaurus to reveal the spiral galaxy M83. Compared to other galaxies, M83 is a close neighbor to the Milky Way, just 15 million light-years away. But this entire system is rapidly moving away from us at the rate of over 500 kilometers every second. Much farther off in space, there are countless more galaxies that are doing the same thing. Here, the Hubble telescope explores a giant elliptical galaxy surrounded by a swarm of smaller neighbors. This cluster of galaxies is more than 30 times farther away from us than M83, and it's receding at more than 10,000 kilometers per second. No matter where we look in the universe, astronomers have found that the farther a galaxy is from us, the faster it's moving away. In the 1920s, it was astronomer Edwin Hubble who first grasped the meaning of this relationship. Hubble realized that all the galaxies must be spreading apart from each other, which makes more distant galaxies appear to recede more quickly. The discovery led to a mind-blowing conclusion. Our universe is not static, but expanding outward in all directions. And as space expands, it's taking the galaxies with it. An expanding universe is a strange idea to come to grips with, but it makes sense. If the universe were static, gravity would have pulled all the galaxies together by now. The expansion explains why this hasn't happened, but it also leads to another powerful conclusion. Because space is growing, it must have been smaller in the past. At some point, the entire universe we can see today was confined in a volume of space smaller than an atom. To have so much matter and energy contained in such a tiny region is unimaginable, but it's this situation that led to the Big Bang. The fiery birth of the universe. Having discovered the Big Bang, astronomers realized they could determine when it happened simply by measuring the rate at which the galaxies are flying apart, and then working backwards. To measure the expansion, astronomers need to look at several galaxies and compare two things: distance and speed. Speed is the easy part. When objects are moving, the light they give off shifts in frequency in direct proportion to speed. This is called the Doppler effect. Here on Earth, it's used to measure the velocity of approaching storms, and it's the principle behind police radar. Measuring the distance to a galaxy is a much tougher problem, and for most of the 20th century, doing it with accuracy was beyond the ability of even the biggest telescopes. That would change when the Hubble Space Telescope was launched.
Liftoff.
Giving astronomers a new and better view of the galaxies. But what they didn't know then is that it would also provide the first clue to the existence of dark energy. By the 1990s, astronomers knew the Hubble Space Telescope was their key to measuring the age of the universe. Freed from the distorting effects of Earth's atmosphere, the Hubble had the power to peer into nearby galaxies and for the first time see individual stars within those galaxies. But astronomers weren't just looking for stars in general. They were hoping to spot Cepheid variables. Cepheid variables are extremely useful because they pulse with a regular cycle, and the brighter they shine, the slower they pulse. So just by timing a Cepheid's pulsations, astronomers can tell how much light it's giving off, and therefore how far away it must be. Starting in 1993, a team of astronomers used the Hubble to hunt for Cepheid variables hidden in nearby galaxies. And they found plenty. The Cepheids gave them a way to measure the distance to each galaxy. Meanwhile, by using the Doppler shift, astronomers could directly measure how fast those same galaxies are receding from us as the universe expands. The final step is just arithmetic. For each galaxy, the speed divided by the distance is the expansion rate of the universe. The more galaxies are measured, the more confident the result. And by knowing how fast the universe is expanding, astronomers could then work out when it all began. It was one of the Hubble's most important results. But when the answer began to emerge in 1994, astronomers were puzzled. Their calculations showed that the universe was less than 12 billion years old. That was younger than earlier estimates, and it didn't match well with some other evidence. Evidence that included white dwarf stars, tiny stellar relics no bigger than Earth that are left over when stars like our Sun burn themselves out. Some of the oldest white dwarf stars can be found inside globular clusters. These are vast, spherical swarms of stars that date back to the formation of our galaxy. Because white dwarf stars cool as time passes, astronomers can look for the coolest, dimmest white dwarfs in a cluster and use them to measure the cluster's age.
But here's the problem. The oldest white dwarfs seem to be more than 12 billion years old. That would make them older than the universe, which doesn't make sense. Somehow, somewhere, astronomers were missing a key piece of information.
In 1998, the missing piece finally turned up, and it changed everything. It involved another way of measuring the distances to the galaxies. This method is based on a particular type of exploding star, which can be seen from a much greater distance than a Cepheid variable. The explosion involves two stars in orbit around each other. One is a tiny white dwarf, the other a massive red giant. In this scenario, hot gas escaping from the giant star is pulled by gravity onto the white dwarf companion. Eventually, so much matter falls onto the white dwarf that it becomes unstable. This triggers a thermonuclear explosion, and the white dwarf goes supernova. What is crucial for astronomers is that the trigger point for the explosion is always the same. And so supernovas of this type always shine at about the same peak brightness. And just as with Cepheid variables, knowing the true brightness of something means knowing its distance. But supernovas can be spotted in galaxies that are even farther away, and their light is reaching us from a more remote time in the past. So by measuring the distance to these far-off supernovas and their host galaxies, astronomers could check to see if the expansion of the universe has changed over time. They were expecting to find the expansion gradually slowing down. That's because the gravity of all the matter and dark matter in the universe acts like a brake pedal on cosmic expansion. The more matter, the more gravity, and the more gravity, the harder it is for things to fly apart. But remarkably, they found the opposite. The expansion of the universe appears to be speeding up. This surprise discovery explains the contradiction over the age of the universe. If space is expanding at a faster rate now than in the past, then it must have taken longer for the universe to reach its current size. That would make the age of the universe greater than 12 billion years. The latest estimate puts it at 13.8 billion years old, which is older than any known star. But if the universe is accelerating, what's causing it? Just like dark matter, there was no way to observe this new phenomenon directly. So cosmologists called it dark energy. Follow-up observations soon confirmed and strengthened the case for dark energy. And by 2011, 3 astronomers involved in the initial find, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize. With the discovery of dark energy, the universe had become a more interesting and more mysterious place. Now it was up to cosmologists to understand what an accelerating universe meant for their theories. And for us. In 2001, cosmologists were given a new way to see dark energy's role in the universe. It was WMAP, an orbiting spacecraft designed to map the cosmic microwave background. The background is a form of relic light that was emitted a few 100,000 years after the Big Bang, when the universe was still white hot. Because of the Doppler shift, this signal is no longer visible to the eye, but it can be detected in the microwave part of the spectrum. One of the signal's key features is that it contains tiny fluctuations that WMAP saw as speckles across the microwave sky. This turned out to be incredibly handy for cosmologists, because the average size of those speckles is related to the total amount of matter and energy in the universe. The data reveal that total is far greater than all the galaxies combined. In fact, all the matter we can see only adds up to a 5% slice of the cosmic pie. But the galaxies are embedded within vast concentrations of dark matter that add up to much more. Altogether, dark matter contributes another 27% to the pie. That still leaves more than 2/3 of the contents of the universe unaccounted for. It's this missing share that cosmologists now say is taken up by dark energy, the mysterious entity that is causing the expansion of the universe to speed up. But to understand what this really means for the universe, we need to know what dark energy is. One possible answer has already been around for about a century. It's called the cosmological constant. It's a mathematical term that Albert Einstein added to his theory of general relativity in order to counterbalance gravity. Einstein used it to explain why all the matter in the universe hadn't converged in one place. But once astronomers discovered the universe was expanding, Einstein realized he didn't need the cosmological constant after all. He even called it his biggest blunder. But with the discovery of dark energy, the cosmological constant was back on the table. The idea is that space has its own built-in energy, and that this energy has a repulsive effect. As the universe expands, more space leads to more repulsion, so the expansion speeds up like a runaway train. So far, the observations agree with this idea. But there are other theories too. For example, it could be that dark energy is the result of a previously undiscovered force of nature. If so, its influence might gradually weaken over time. Or there could be a more chilling possibility. Rather than a constant, the acceleration of the universe could itself be accelerated. In that case, it will eventually overtake all other forces, pulling apart individual galaxies, stars, and finally atoms. Cosmologists call this scenario the Big Rip. To help distinguish between these possibilities, a US-led team of scientists has launched the Dark Energy Survey. This project uses a special camera installed on a telescope in Chile that can look for evidence of dark energy in a number of ways. One of the ways involves probing the large-scale structure of the universe. This structure looks like a cosmic spiderweb, with all the galaxies concentrated in enormous strands that separate empty voids millions of light years across. If measured carefully, the regular spacing of these strands can be used like a giant ruler to measure how the expansion of space has changed over time. The Dark Energy Survey began in late 2013. To help pin down dark energy, scientists hope to measure as many as 300 million galaxies over a 5-year period. Meanwhile, in Canada, astronomers have realized that they can do with radio waves what the dark energy camera does with light. Their project involves a series of trough-like radio antennas, each one 100 meters long. The troughs are used to map the distribution of distant clouds of intergalactic hydrogen, which pass overhead as the Earth turns. The advantage of this method is that the hydrogen clouds are easier to detect than individual galaxies, so astronomers can use them to peer back to earlier times in cosmic history, when it might be easier to distinguish between rival theories of dark energy. Looking further ahead, the European Space Agency has proposed a space telescope named Euclid that is specially designed for the task of measuring dark energy. It could launch as early as 2020. And NASA is pursuing a dark energy telescope of its own, called WFIRST, currently set to launch in 2024.
20 years ago, no one knew dark energy existed. Now, understanding it has become our cosmic priority. And there's something very appropriate about that.
Billions of years ago, any civilizations that were around may not have discovered dark energy because the acceleration of the universe was still too small to notice at that time. And trillions of years from now, future civilizations won't see it either. By then, space will be growing so fast that light from the cosmic background, along with most of the galaxies, won't be able to cross it. As those galaxies disappear over the cosmic horizon, they'll take the evidence for dark energy along with them. This is perhaps the greatest revelation of all. Not only is there much more to understand about the universe than astronomers once thought, it appears that that understanding is a limited time offer. On a day that begins like any other, dawn breaks and the sun climbs up into the eastern sky. But as its rays illuminate the world, no one senses that a strange transformation is about to begin. Gradually, a slight indentation appears in the great round disk of the sun. Minute by minute it grows, until, after an hour, more than half the sun has disappeared. Now the day has become noticeably less bright, and shadows are getting sharper. As the sun narrows to a slender crescent, birds become agitated, confused by what seems like night arriving far too soon. Then darkness descends, and up above there's a strange, almost magical spectacle. In place of the sun, it looks like a perfectly round black hole has been punched in the sky. All around it, there's a ghostly white aura. The world is captivated by the ethereal beauty of a total eclipse of the sun.
We can only imagine how our prehistoric ancestors might have reacted to this incredible natural phenomenon, especially if it came upon them without warning. To them, a total eclipse might have seemed like the end of the world, or perhaps a sign from the gods.
Yet, as impressive as an eclipse can be, even more impressive is the fact that ancient people came to understand what causes them, and even how to predict them. The key is realizing that eclipses involve both the sun and the moon. A solar eclipse occurs when the moon passes in front of the sun, casting its shadow on Earth's surface. And when the moon moves to the opposite side of its orbit, so that it travels through Earth's shadow, the result is a lunar eclipse. But knowing exactly when an eclipse will take place is a bit more challenging. Although the moon circles around Earth once a month, eclipses are far less common. This is because a slight tilt in the moon's orbit means that most of the time, the shadows cast by the moon and the Earth don't line up in quite the right way. In any given year, only 4 or 5 eclipses are possible, usually in pairs, one lunar and one solar. Some of these eclipses are partial, which means that only part of the sun is blocked or only part of the moon is shadowed. If not expected, such eclipses can easily pass unnoticed. Other eclipses happen when the weather is overcast, or they may appear in remote corners of the world, such as the high Arctic or Antarctica, where few people are watching. When all of these variables are factored in, it means very few people see more than a handful of eclipses over the course of a lifetime. Of these, most will be lunar eclipses, simply because when a lunar eclipse is underway, it can be seen anywhere that the moon is visible, roughly half the world at any given time. This means that our prehistoric ancestors almost certainly knew that eclipses can happen. But it wasn't until ancient skywatchers started keeping careful records over many generations that a longer-term pattern in eclipses began to emerge. That pattern is called the Saros cycle, and it was first discovered sometime after 750 BC by astronomers who lived in Mesopotamia, modern-day Iraq. They were among the first to notice that lunar eclipses with very similar characteristics seem to repeat every 6,585 days. That's just over 18 years, a period known as one Saros. Solar eclipses follow this pattern too, but it was harder for ancient people to detect this because solar eclipses in the same 18-year series happen in different parts of the world. Here, for example, is a spectacular image of a total eclipse of the sun observed in Mexico in July 1991. The next eclipse in this series happened right on schedule 18 years later in July 2009, but it was seen in China. It takes 3 Saros, about 54 years, for a similar solar eclipse to appear in roughly the same part of the world. Nevertheless, it's recorded that by around 585 BC, the Greek astronomer Thales successfully predicted a solar eclipse. Today, such ancient records can serve a scientific purpose. That's because astronomers can compare where eclipses were seen long ago to where the calculations say they should have been seen. The differences reveal slight changes in Earth's rotation over thousands of years. Today, scientists can predict exactly where and when eclipses will be seen, but that doesn't make them any less interesting. Instead, the mystery of eclipses has been replaced by anticipation, and for many, a deep desire to witness one of the most breathtaking sights in nature. Although the timing of an eclipse can be predicted to the second, eclipse watchers know that the end result can still be a surprise. For total eclipses of the moon, most of the surprise comes from Earth's atmosphere. As the lunar eclipse proceeds, the moon first slides into Earth's outer shadow, known as the penumbra, where only a portion of the sun's light is prevented from reaching the moon. This penumbral phase of the eclipse is barely noticeable. Later, the moon may hit the inner shadow, the umbra. At this point, a partial lunar eclipse begins, with some of the moon clearly in darkness. But even if the lunar eclipse is total and the moon enters the umbra completely, it doesn't disappear. Instead, a portion of the sun's light is refracted or bent as it passes through Earth's atmosphere and then redirected toward the moon. The light has a reddish tinge because it's red sunlight that can pass through the atmosphere most easily, just as it does during sunset. But how bright and how red the eclipsed moon appears depends strongly on how much sunlight gets through. When Earth's upper atmosphere is clear, the moon takes on a coppery color. When it's not so clear, the result is a dark crimson or even brownish lunar eclipse. This was proved to dramatic effect after the 1991 eruption of Mount Pinatubo in the Philippines. It was the largest volcanic eruption in over a century, and it lofted an estimated 20 tons of sulfur dioxide into the atmosphere. This produced a global haze layer that lasted for months. And when a total lunar eclipse occurred in December 1992, the moon was so dark it nearly disappeared.
Solar eclipses also vary in their appearance, but the reasons have more to do with observer location, and being in the right place at the right time usually takes some planning.
During a solar eclipse, the moon's shadow sweeps across Earth's surface. Any place where the shadow hits will at least see a partial eclipse of the sun. But to see a total solar eclipse, you need to be standing near the center of the moon's shadow, in a zone that's often only 100 kilometers or so wide, depending on latitude. This central part of the shadow traces a long, narrow track called the path of totality. On either side of the path, the solar eclipse is only partial. Inside it, viewers are treated to the full spectacle of a total solar eclipse. Getting onto the path of totality is well worth it, because it's only here that the most dramatic effects of a solar eclipse can be experienced. And the difference between a partial and a total eclipse of the sun is literally night and day. Even when it's only partly visible, the sun's blazing surface, known as the photosphere, easily outshines anything else in the sky. But once the photosphere is fully covered by the moon, the sun's wispy outer atmosphere appears. This is the corona. It's made up of ionized particles that have been blasted from the photosphere and heated to over 1 million degrees. The corona's feather-like structure is shaped by a powerful magnetic field, which is generated inside the sun and extends far out into space. The field changes with an 11-year cycle that relates to the appearance of sunspots, darker, cooler regions on the sun's surface. When the sunspot cycle is at its maximum, the corona tends to be round and symmetrical. When there are few sunspots, it becomes long and spindly. It's this elongated version of the corona that may have led to the ancient Egyptian symbol of the winged sun. A total eclipse also offers a rare chance to study the long loops and filaments of plasma that are caught up in the sun's magnetic field. These are called solar prominences. In the middle of a total eclipse, when the sun is completely covered, prominences can often be seen glowing ruby red around the moon's dark perimeter. Together, all of these features add up to a remarkable sight that's different every time. And it's also fleeting. Because of the speed at which the moon's shadow passes across Earth's surface, a total eclipse generally only lasts a few minutes at most. In the final second, as sunlight creeps around the moon's receding edge, a sudden flare shines forth, creating the illusion of a diamond ring in the sky. For those watching, the diamond ring is like a parting gift from the solar eclipse, and a confirmation that something truly incredible has taken place. On the dry, frigid plains of Mars, the sun shines pale and weak. But while the sun is far away, solar eclipses are not. Mars is orbited by 2 small moons, both of which can cross in front of the sun as seen from the Martian surface. No human has ever experienced this, but NASA's Curiosity rover has, and it's recorded them. This is Curiosity's view of a solar eclipse on Mars. Since the moons are small and irregular in shape, the sun is never blocked completely. Although interesting, the effects of a Martian solar eclipse are not especially dramatic. On Earth, it's a very different story. Here, eclipses have a history of making deep impressions wherever they appear. In some cases, they have changed the course of history. In March 1504, Christopher Columbus was beached in Jamaica when a book of astronomical tables alerted him to an approaching lunar eclipse. He used the eclipse to his advantage, impressing the local tribespeople with his apparent control of the event and persuading them to keep his crew supplied with food. 2 centuries later, in response to a challenge from U.S. authorities, a Shawnee spiritual leader named Tenskwatawa motivated his followers by forecasting the total solar eclipse of June 1806. Under the leadership of his brother Tecumseh, those followers would go on to play a key role in the War of 1812. Meanwhile, the Spanish astronomer José Joaquín de Ferrer traveled to the U.S. to observe the same 1806 eclipse. It's thought that he coined the term corona to describe what he saw around the eclipsed sun. Eclipse science got another boost 30 years later, when Francis Bailey, a retired stockbroker with no formal training in astronomy, traveled to Scotland to observe a solar eclipse. The eclipse was not total, because at that moment the moon was at a more distant point in its orbit than usual. That meant it was too small to cover the sun completely. So Bailey saw what is now called an annular eclipse, during which the exposed portion of the sun forms a ring or annulus around the moon. Bailey noticed that in some places the ring was so thin that the silhouettes of mountains on the moon broke through it, turning the ring into a string of beads. This effect has been called Bailey's beads ever since. Bailey's account of the phenomenon was so intriguing that by 1842 the next eclipse in Europe drew many more astronomers. Eclipse science was shifting into high gear. Over the following decades, several key discoveries were made during eclipses of the sun. But what may be the most scientifically significant eclipse of all time came in 1919. Only a few years earlier, Albert Einstein had published his theory of general relativity, which united space and time and predicted that gravity bends light. The theory offered a completely new way of thinking about the universe. The challenge was finding a way to test it. It was soon realized that during a total solar eclipse, it might be possible to see if the sun's gravity had an effect on the incoming light of background stars, stars that would normally be too hard to observe while the sun is shining nearby. In the spring of 1919, an expedition led by British astronomer Arthur Eddington set out to put Einstein to the test. Watching from an island off the west coast of Africa, Eddington woke up on the day of the eclipse, May 29th, to overcast skies and heavy rain. Miraculously, just 18 minutes before totality, the clouds began to break up. By observing through clear patches, Eddington was able to make the crucial measurement. When Eddington presented his results back in England, he showed that the background stars had shifted just as predicted by Einstein's theory. At first, not all of his colleagues were convinced, but the news caused a global sensation, and overnight, Einstein became a household name. Today, the effect of gravity on light has become a powerful tool in cosmology. It can be used to turn vast clusters of galaxies into enormous natural lenses that can magnify our view of the more distant universe. But it all started with a solar eclipse.
100 years after Eddington, eclipse chasing is no longer just for scientists. It's practically a sport. Each time there's a total solar eclipse in an interesting part of the world, thousands travel just to be there, and the experience can be truly amazing.
And someday, that experience will no longer exist. Solar eclipses happen because the sun and the moon appear to be almost exactly the same size in our sky. The result is pure magic. But it's also a pure coincidence. As ancient eclipse records show us, the Earth's rotation is gradually slowing down over time. In response, the moon is gradually moving further away. Eventually, the moon will no longer appear large enough to cover the sun entirely. Astronomers estimate that the last total solar eclipse in Earth's history will happen about 600 million years from now. that still leaves us with many more chances to see one of the most incredible sights in the universe. But why wait? Eclipses are a natural wonder that seem tailor-made for humans to enjoy. And they're a reminder that even here on Earth, we live in a larger cosmic reality, a reality that seems unlimited in its capacity to enchant us. As a species, we have always been fascinated by the stars. When twilight deepens and thousands of pinpoints of light appear in the night sky, we are naturally moved by the wonder of it all, and by our desire to understand it. But for all those who ponder the nature of the stars, the universe poses a special challenge, because how can we hope to understand what we cannot touch?
The remoteness of the stars means that we can't just reach out and grab them to see what they're made of. But remoteness is not an insurmountable barrier to understanding. Over the centuries, astronomers have learned that the stars do reveal their secrets when we learn to look at them in the right way.
At first, ancient thinkers compared the stars to what they knew from everyday life. Around 450 BC, the Greek philosopher Anaxagoras reasoned that the stars must be like stones, glowing with extreme heat, but too far away for us to feel their warmth. In fact, there was an element of truth to this. But when Aristotle looked to the stars a century later, he disagreed. Aristotle said the stars couldn't be made of fire, stone, or anything that we experience on Earth, because stars behave differently. Instead of moving in straight lines, like falling objects, the stars spin in circles around us as they rise and set each night. And the stars never seem to change. Aristotle thought they were eternal, made out of a heavenly substance called the ether. Aristotle's ideas would hold sway for the next 18 centuries until astronomers started to see things differently. First, they realized that the stars aren't spinning in circles after all. It's we who are spinning by living on a rotating planet that is also following a curving path around the sun. Then, in 1572, a brilliant new star suddenly appeared in the constellation Cassiopeia. For a time, it outshone every other star in the sky. After many months, it gradually faded from sight. Today, we know this celestial interloper was a supernova, the explosive death of a massive star. The remains of that explosion can still be seen as a vast bubble in space, over 8,000 light-years away. But what really mattered to astronomers back then was that the supernova proved that even stars can sometimes change. Then came the telescope, the device that revolutionized astronomy by making distant objects appear closer. Through the telescope, the planets were transformed from dots in the sky into full-fledged worlds. The telescope also confirmed that the stars were much further away than ancient astronomers had ever imagined. Far enough to be distant versions of our own sun. Increasingly, it no longer made sense to think of heaven and earth as separate. Both are governed by the same principles. In 1687, Isaac Newton demonstrated this once and for all by showing that his famous law of gravity applies to the moon and planets just as it does to apples falling from a tree. But it was another discovery of Newton's that would ultimately allow astronomers to learn what stars are made of. In his book on optics, published in 1704, Newton showed how white light is a combination of all the colors. With the help of a prism of glass, those colors can be separated into a spectrum, like a rainbow. Newton explained how rainbows work, but it wasn't until 1802 that an English chemist named William Wollaston took the spectrum one step further. Wollaston improved the separation of the colors of light by first passing sunlight through a narrow slit and then a prism. That's when he noticed that the sun's spectrum contained a few thin, dark lines. Wollaston thought the lines were borders separating the colors, but he had only seen the tip of the iceberg. In 1814, a German instrument maker named Josef Fraunhofer invented a device for measuring the refraction of light through different types of glass. When used with sunlight, the device allowed Fraunhofer to see the same dark lines in the spectrum that Wollaston had seen. But he also saw hundreds more. Fraunhofer didn't know it yet, but his device, called the spectroscope, would eventually be used to crack the mystery of what the sun and the stars are made of. But not until someone could figure out how to read the hidden message in those lines and turn a celestial barcode into a new form of astronomical knowledge. In the scientific journey, there have always been moments when progress has seemed impossible. That was the case in 1835, when the French philosopher Auguste Comte wrote that the chemical composition of the stars would forever be beyond the limits of human knowledge. Comte assumed that scientists would have to travel to the stars to learn what they're made of. But thanks to the invention of the spectroscope, he was soon to be proven wrong. The spectroscope works by dispersing light into a spectrum of colors, from red to violet. It also shows that the sun's spectrum is riddled with fine dark lines. Because light is a wave, the lines mark particular wavelengths where some of the energy in the sun's light has gone missing. But where did it go? In the 1850s, two German physicists, Robert Bunsen and Gustav Kirchhoff, teamed up to find out. Their experiments showed that when light passes through a gas, the atoms in the gas absorb some of the light, but only at certain specific wavelengths, which depend on the properties of that particular type of atom. That explains the lines in the sun's spectrum, which are called absorption lines. Kirchhoff and Bunsen realized the lines act as a chemical fingerprint because they reveal which gases are present in the sun's atmosphere. But that's only half the story. When atoms are energized in the right way, they can emit light too. This creates a spectrum of bright lines, known as emission lines, which are the counterparts to the dark absorption lines.
For astronomers, all of these spectral lines, both bright and dark, revealed a link between the Earth and sky. In the laboratory, they could measure the spectra of gases and flames using known materials. Then they could compare these results to the spectra of the sun and stars. For the first time, the chemistry of the universe was on display.
Starting in 1862, the English astronomer William Huggins was among the first to attach a spectroscope to his telescope and explore the heavens in a new way. He was later joined by his wife and scientific collaborator, Margaret. From their home-built observatory near London, Huggins recorded the spectra of many stars and other celestial objects. Among his targets was the Great Nebula in Orion, a misty patch of light located near the stars of Orion's belt. Huggins found that the nebula's spectrum consisted entirely of bright emission lines, especially lines corresponding to hydrogen. Here was evidence that the nebula was really a vast cloud of glowing gas, perhaps a cloud that might someday condense to form new stars. In 1864, Huggins saw something a bit different when he turned his spectroscope on the Cat's Eye Nebula, an expanding shell of gas blown off of a dying star. The Cat's Eye produced a bright green emission line that didn't seem to correspond to any known element. Huggins dubbed the mystery substance nebulium. It would take over 60 years before astronomers realized that the green line is produced by atoms of oxygen with 2 electrons stripped away. This energized state reveals the high temperature and low pressure environment within the nebula, which is expanding at nearly 60,000 kilometers per hour. In 1868, the spectroscope really did lead to the discovery of something entirely new. In August of that year, French astronomer Jules Janssen used a spectroscope during a total eclipse of the sun. Janssen was hoping to isolate the light from a solar prominence, a glowing ribbon of ionized gas suspended in the sun's powerful magnetic field. Normally, prominences are impossible to see because the surface of the sun is so bright. But during a total eclipse, any large prominences on the edge of the sun are immediately visible to the eye. And when Janssen turned his spectroscope on one of them, he saw some emission lines he didn't recognize. In fact, they didn't correspond to any known gas. Janssen soon found he could spot the same emission lines in the sun's spectrum without needing an eclipse to do it. At the same time, in England, an astronomer named Norman Lockyer had seen the emission lines too. Like Janssen, Lockyer recognized that the lines were produced by a previously unknown element. He named it helium, after Helios, the Greek god of the sun. It would take 27 more years before the existence of helium was finally confirmed in the laboratory, but its discovery on the Sun made Jensen and Lockyer famous. Lockyer went on to become the founding editor of the scientific journal Nature. By the end of the 19th century, the spectroscope had proved its worth in decoding the chemistry of the Sun and the stars. But its greatest triumph was still to come. By 1925, it seemed that the quest to understand what stars are made of had come full circle. 24 centuries earlier, Anaxagoras had written that stars are fiery stones. Now the spectroscope was suggesting something similar. By pointing it at the Sun and at distant stars, astronomers could see spectral lines that corresponded to sodium, calcium, magnesium, iron, and many other elements that are commonly found in minerals on Earth. This persuaded the American astronomer Henry Norris Russell to suggest that if Earth's crust were heated up to the Sun's temperature, it would share the Sun's spectrum. Russell was a leading authority on stars, and his view defined the scientific mainstream. But Russell's universe was about to change. The groundwork for that change had been laid years earlier by a remarkable group of women in Cambridge, Massachusetts, who were hired to work at the Harvard College Observatory. In an age before computers, the observatory's director, E.E. Pickering, was dealing with a vast flood of new data from the heavens. The development of photography and spectroscopy together meant that the spectra of thousands upon thousands of stars could now be captured and recorded on photographic plates. It was a data overload, and Pickering needed help. He didn't have the budget to hire an army of astronomers. So in 1881, Pickering hired his housekeeper, Wilhelmina Fleming. Fleming had been a schoolteacher in Scotland, and she soon mastered the art of cataloging stars according to their spectral lines. She came up with her own classification scheme and ultimately examined some 10,000 individual stars on photographic plates. Pickering hired more women to help and put Fleming in charge. Over the next 30 years, they would lay the foundations for modern astrophysics. One of the most important members of the team was Annie Jump Cannon, who arrived at the observatory in 1896. As she gained experience, Cannon became truly prolific at cataloging stars based on their spectra. At her best, she could catalog 3 stars per minute. It's estimated that over her lifetime, she classified about 500,000 stars by eye, more than anyone else in history. As she worked, Cannon hit upon a more advanced system for classifying the stars. Her approach showed that there was a progression in the spectral lines as one moved from star type to star type, with some lines becoming stronger and others fading away. This was an important clue, but it would take another astronomer to understand what it meant. Cecilia Payne grew up in England, where she became fascinated with the science of the stars. But she soon learned that opportunities for women in astronomy were virtually non-existent. In 1923, Payne arrived at Harvard College Observatory to join a newly launched graduate program there. Working with Cannon's data, Payne began to see the underlying physics behind the classification scheme. She realized that a spectrum is really a way to measure a star's temperature. Stars at different temperatures energize the atoms of various elements in different ways, leading to a unique set of spectral lines. But Payne's analysis also showed something else. The dominant element in all of the stars appeared to be hydrogen. In 1925, Payne summarized her findings in her PhD thesis. But when Henry Norris Russell read an advanced copy, he thought her conclusion about hydrogen had to be wrong. Payne then added a line to the thesis that undermined her boldest discovery. Within 4 years, Russell realized it was he who was wrong, and he admitted it.
Cecilia Payne's astonishing insight was correct. Today, astronomers know that hydrogen is the most abundant element in the stars, and that points the way to an amazing scientific story.
It's now clear that stars are born out of clouds of hydrogen gas, like the Orion Nebula that William Huggins once studied. Once they form, the stars shine because of nuclear reactions that turn the hydrogen into helium and other heavier elements. Eventually, stars die, and the elements they've created are released back into space, just as they are in the Cat's Eye Nebula. In the process, the stars are seeding the universe with the raw material needed to produce planets and life. This is the great secret that the spectroscope has revealed. A secret unraveled over a century and a half by a succession of remarkable men and women. Thanks to them, we now know what stars are made of. But in a very real sense, we've also learned that we are made of stars. Gazing into the night sky, it's easy to be awed by the grandeur of our universe. It's not just that space is big, it's that our place in it is so little. And as our knowledge of the universe has grown, so too has the realization that most of it is completely unsuitable for life. Between the searing heat of the stars and the frigid depths of space, it's clear that life as we know it can only survive by clinging to those few rocky planets that are lucky enough to exist in the narrow zone between too hot and too cold. While the rest of the universe can be breathtakingly beautiful, it seems utterly indifferent to our existence. But what if it's just the opposite? What if all this is here because we're here?
It's called the anthropic principle. It's the idea that our cosmic reality is a product of the fact that we're living in it. That may seem like a backwards argument, but some cosmologists say it may be the only way to explain why the universe is the way it is.
In ancient times, the universe didn't need that kind of explaining. With so much order and complexity in the world, it was logical to imagine that a divine being of some kind just made it that way. Yet in ancient Greece, philosophers took a different path. They tried to explain the universe in terms of natural laws. In many cases, they guessed wrong about the causes of various phenomena, and also about our place in the universe. For example, Aristotle argued that Earth had to be at the center of the cosmos, with the stars and planets circling around it. But while this conclusion was mistaken, the approach taken by Aristotle and other philosophers would eventually develop into modern science, with its emphasis on observation and reasoning. It was a progression that took many centuries, but by the early 1500s, our current understanding of the universe was starting to emerge. The key step was taken by Nicholas Copernicus, a Polish church official and administrator who was also a brilliant astronomer. Copernicus realized that the motions of the planets made a lot more sense if the Sun, rather than Earth, was at the center of the solar system. When Copernicus's ideas were published after his death in 1543, the scientific revolution began. At first, the Copernican system was controversial for religious reasons, but also because it seemed to defy common sense. After all, to any observer standing on solid ground and looking up at the night sky, it really does seem as though Earth is at the center. But Copernicus's great achievement was finding a deeper logic to the natural order of things. That logic tells us that it makes little sense for Earth to be at the center of everything, because that would mean humans just happen to be living at the most special place in the universe. For centuries ever since, astronomers have embraced what's now known as the Copernican principle. The principle states that our place in the universe is very unlikely to be uniquely special. Rather, the way we perceive the universe is likely pretty close to what other observers would experience from their locations. In the 20th century, this premise became the bedrock of modern cosmology. Once astronomers realized that nearly all the galaxies are moving away from us, the Copernican principle pointed the way to a dramatic discovery. It's not that we're at a special place that the galaxies just happen to be receding from. Rather, all of the galaxies must be moving away from each other as the entire universe expands. Our location may have its own particular details, but the universe looks about the same no matter where you are. As telescopes improved, the Copernican principle continued to fit the accumulation of evidence. The universe has turned out to be full of galaxies similar to our own, stretching off in all directions for billions of light years. We're not at the center, and neither is anyone else, because as far as we can see, the universe has no center and no preferred direction to look. But cosmologists were beginning to notice something curious. While our view of the universe may not be special, the universe as a whole does appear to be very special indeed. What makes it special are the laws of physics that govern our reality. And as cosmologists started to consider these laws more closely, they found themselves heading in a new direction, one that for the first time in nearly 500 years was leading them away from Copernicus. Our universe is a place of extraordinary diversity. And from the planets of our solar system to the distant galaxies, the more we explore, the more variety we see. But underlying this variety is a deeper, simpler picture. So far, just about everything we've observed can be explained with a basic set of natural laws. These are the rules that dictate how matter and energy behave. They include the properties of fundamental particles and the forces that operate between them. But while these rules explain a lot, nothing seems to explain why the rules are so perfectly set up to produce a universe that can support life. Take gravity, for example. Relative to all the other forces in nature, it's extremely weak. That's why a toy magnet can easily overcome the gravity of the entire Earth and lift up a paper clip. But if gravity were any stronger, the result would be a disaster. In such a universe, the matter inside stars would be squeezed together more tightly. This would speed up nuclear reactions and cause stars to burn out sooner. With just a modest increase in the force of gravity, no star would last long enough for life to appear and evolve. Yet, if gravity were much weaker, then stars wouldn't shine at all. In the same way, particle physics is full of what seem to be chance numbers and relationships that we depend on for our existence. The neutron and the proton are almost equal in mass, but the neutron is slightly heavier, by about 0.14%. If it were the other way around, atoms wouldn't exist. A more subtle example suggests that our universe is perfect for the emergence of life based on carbon, the only kind of life we know. Carbon atoms have the property that they can readily form long chains, which are essential for large organic molecules, the kind of molecules needed to make working cells. But carbon forms only in the cores of stars. And when physicists began to work out exactly how that happens, they discovered a curious puzzle. It takes 12 particles to make the nucleus of a carbon atom, 6 protons and 6 neutrons. Stars build up carbon by starting with helium. Each helium nucleus has 2 protons and 2 neutrons. First, 2 heliums come together to form beryllium-8. Beryllium-8 is highly unstable and likely to fall apart in less than a trillionth of a second unless one more helium comes along. In stars, that happens often enough. But here's the problem. When you add beryllium and helium together, the result has too much energy. Instead of making carbon, they should just fly apart. In 1953, the British astronomer Fred Hoyle realized there was a way around this problem. He predicted there was an excited form of carbon that closely matched the higher energy level of beryllium plus helium. Hoyle was right. the excited carbon state was discovered soon after his prediction. Its existence makes it far more likely that beryllium and helium will morph into carbon once they've come together. But why is the energized state of carbon just right to allow this to happen? To understand why this is a problem, imagine pressing the emergency button to stop a fast-moving elevator. Then the door opens, and you discover that the place where the elevator has stopped perfectly matches a floor where people can step off. In other words, it's sheer coincidence. Yet it's a coincidence that we owe our lives to.
Over the years, physicists have come across other examples like this. Cases where if the numbers were changed just slightly, we wouldn't be here. No one would be here. It's this realization that's brought us to the anthropic principle.
The term was coined in 1973 by the Australian cosmologist Brandon Carter, who divided the anthropic principle into two versions. The weak version is simply the argument that our place and time in the universe is special because it's compatible with the existence of life. If it wasn't, we wouldn't be around to experience it. But there's a stronger version too, which suggests that the universe isn't possible unless at some point it allows life to evolve. Otherwise, the laws of physics are just too much of a coincidence. Once Carter formulated these definitions, it became clear that the anthropic principle presents a challenge to the traditional way of doing science. Ever since Copernicus, astronomers have been working on the premise that the universe is independent of our presence in it. With this premise in mind, many cosmologists resisted the anthropic principle, hoping that scientific progress would eventually lead us to a better understanding of the laws of nature. But then, a surprising development put the anthropic principle back in the spotlight, along with a stunning theory about the true nature of our cosmic reality. In 1998, astronomers made a discovery that would forever change our understanding of the universe. They found evidence for dark energy, a mysterious phenomenon that permeates all of space and is causing the expansion of the universe to speed up. This is big news because it helps explain everything from the age of the universe to its long-term future. But the presence of dark energy also carries huge implications for the anthropic principle. Of all the cosmic coincidences that seem to make our universe suitable for life, dark energy may be the biggest coincidence of all. This is because the density of dark energy is so extraordinarily small. Just a tiny fraction of a fraction of a fraction more than zero. So far, there's nothing in the laws of physics that predicts why dark energy density should have such a minuscule value. It seems to be completely arbitrary. Yet with just a little more dark energy, the early universe would have expanded too quickly for matter to come together to form galaxies. Without galaxies, there would be no stars, no planets, and no possibility of life. For scientists, this is a philosophical problem, because how can you explain a universe that seems to be tailor-made for us? In fact, the discovery of dark energy has now been used in some religious circles as an argument for why there must be a divine creator. But scientists have found another way of looking at the problem. Consider the case of Earth in our solar system. Among the planets, Earth seems uniquely well positioned for life. If it were a little bit closer to the sun, it would be too hot. If it were a little bit farther, it would be too cold. There's no reason for Earth to be at just the right distance from the sun for life to flourish. So is this another example where scientists have to take the anthropic principle into account? The answer is no, for a very obvious reason. Earth is not the only planet. In our solar system, there are several other planets, and many more have been discovered around other stars. It's estimated that there are billions of planets in our Milky Way alone, each with its own characteristics and temperature. That means Earth is no coincidence. It's just one of billions of possibilities. And since we can only exist on a planet like Earth, it makes sense that this is the kind of planet we happen to be living on. Now, cosmologists have applied the same reasoning as a way of dealing with the anthropic principle. Because what if our universe is not the only one? Instead of one universe with one set of physical laws that just coincidentally happen to be perfect for life, what if there are countless other universes in which the laws of physics can come in any possible form? This larger picture of reality has become so compelling that cosmologists have given it a name. It's called the multiverse. If it's true, then as vast as our universe may seem to us, it's merely a bubble in a multi-dimensional cosmos where other universes are popping up all the time, each with its own value for dark energy. Since only a very, very few of those universes would be livable, then it's no coincidence that we find ourselves living in one. It's a startling conclusion, and even though it hasn't been proven, it's supported by two different fields of research. One is string theory. It's a mathematical method of explaining the laws of nature that turns out to have a vast number of possible solutions. Some theorists now say all those different solutions correspond to different universes in the multiverse. Secondly, scientists who are probing the early universe have found that what they're seeing is consistent with a theory called cosmic inflation. The idea is that our universe emerged from a small patch of space that released energy by inflating at an exponential rate. If that's correct, then other universes should be doing the same thing in an eternally inflating multiverse.
There are plenty of reasons to be cautious about this picture. For one thing, it means we have to conjure up a vast number of other universes just to explain this one. And if it's true, it means there will never be one set of physical laws that predicts our reality, because in the multiverse, so many other realities are equally possible.
As strange as it seems, this picture may be our only way of explaining what astronomers have found. Because of the multiverse, the anthropic principle is now at the center of one of the most fascinating debates in the history of science. It's a debate that involves everything we know about the universe and possibly everything we can know. Where that debate will lead us is still unknown, but it will surely be shaped by what we learn as astronomers continue to probe the universe to its limits. In the meantime, we already know that despite the Copernican principle, there is one way in which our perspective on the universe is special. Because it's only in our lifetime that humanity finally has the tools to reveal how rich and potentially vast our cosmic vista truly is.